So on the code side, basically I'm using the pre-canned libraries for ESP32 Wi-Fi, web server, the OLED, and I think that's it. So I couldn't actually use the pre-canned Modbus libraries that other people have created, and I believe that that has to do with the ESP32, at least the version that I have is dual core, and there's all kinds of weird timing stuff that happens. I think it runs free RTOS, real-time operating system, in the background, and the task scheduler tends to get things out of sync, and that's not just on free RTOS. I've had the same things happen in Windows many times. Whenever you go to a multi-threaded environment, especially with multiple cores, sometimes there are essentially collisions. There's race condition. One thing is told to start at the exact same time as another, and if you do that 10 times in a row, even though they're both triggered at the exact same time and everything's deterministic, sometimes the second thing will start before the first. And I've noticed that even whenever this thing's connecting to the Wi-Fi, sometimes it'll boot up and instantly connect, and other times it will boot up and say connecting to with your SSID. So it did actually go out and get the information, but it's almost like the main loop that we have in our code got started before the Wi-Fi library fully initialized, so then it never goes through its full connection. So as I mentioned, I found another guy's video that gave me some information on the timing sequence for this, and that made a lot more sense to me since I already knew how the Modbus packets were structured, and I'd worked with the Yaskawas in the past. So all this code is uploaded to GitHub. My username, Windwalk06, goes back to when I was like 12 or 13, I don't know, 2006. I played a lot of video games, and I had to pick a gamer handle, and it's basically stuck with me ever since. So anyway, I have this on GitHub /windwalk06/ESP32_Yaskawa V1000, which is the model of the VFD. There's a great wiki on there. I say great, I made it, so it's probably not, but there's a wiki on there that has information about the boards I used, where to find them on like Amazon, the original project that was on Instructables that I used for figuring out how to use the OLED and all that. And then I linked to the video of the guy who was telling me about the timing sequence. So all that's up there. I will continue to update the project. I have future plans of changing the way this thing works, because obviously this was just a proof of concept. But if we go back to the code, on the web server side, basically whenever you pull up the web page and you click on something, so 192.168.0.106, if you click on run reverse, which you might even be able to hear it start up in the background, maybe not, you notice the web page says running reverse, and as you saw earlier, the OLED also says run reverse, and the motor starts turning. So what's making all that happen? I'm going to go back and stop it real quick. So if we go to the code here, basically I have 4 conditions from the server. In the loop, it's constantly running handle server. So the server is checking for any of these conditions, and once they get triggered, it triggers a function to do a thing. So in this case, whenever we do handle root, it's just building that initial web page that we saw and passing that as string information to the server. The handle forward, handle reverse, and stop are all calling functions, something a little different. If you notice this one, start true, start false, that true and false is a direction, and then that 6000 is 60 hertz. Basically, anytime we're talking to one of the registers on the VFD, we just don't acknowledge decimal places. So in the VFD, that register has a setting for 60.00, but we just tell it 6000. Anyway, so these 3 functions for start and stop, I guess 2 functions with different arguments. What are they actually doing? So if we go up and find them here real quick, if we go right past them and then go back down and find them here real quick, FN stop, perfect. So there's a struct created. A struct is a class without functions, basically. It's just a data object in memory. We have this struct that has a spot for an ID, function code, an address, data length, and then some sort of a buffer. I think it's this might even be an int buffer, but a character buffer, a string of bytes in space. So whenever we do click that stop button, the first thing it does is calls this stop function, which constructs this packet that says for the given slave ID, which is the VFD's H501 parameter for its slave ID, which is 6 in this instance, we are going to write multiple registers, which means that we're going to send it more than one, potentially 16-bit register of information that we want it to do something with. Then an address for that start register. So in the instance that we were actually using multiple registers, efficiently instead of just using one like I am, we could find two contiguous sections of memory registers on the VFD that were one right after another, and we could update them both in the same packet. So rather than using a single 16-bit address or register, we could use two, and then as long as the starting address, once it got through the first 16 bits, the next 16-bit address was the second thing that we wanted to update, then we could send that information all at once in one packet, which cuts down on potentials for interference and all that kind of thing. So that would be much more efficient. What I'm doing is basically saying we're going to write multiple registers, but then I'm only giving it a data length of one 16-bit register. So I have all this extra information in this packet that doesn't necessarily need to be there because I'm not actually making use of it. I could use write single, and then it would know just based on that header that it was only going to get 16 bits and then a stop bit after that. And then basically we buffer this all to this character buffer and send it to the write function. So the write function then must do some sort of writing. Basically, so we've passed a pointer to this write function that goes to a struct that we just created. And then based on the function code, we come down here to this switch statement. We go ahead and queue up the ID and the function into the serial buffer, but then we need to figure out the rest of the information. So we go to the switch statement, which has all of the, not all of actually, but 4 of the potential function codes that I would want to use, one of which is write multiple registers. So in this write multiple register, basically we're transferring information, a new buffer. We're bit shifting because I think I'm not actually sure why I did that. Maybe I used an integer array the first time, and now I've got to use a character array, so I went from 16 bits to 8. I can't exactly remember, but it's a good example of bit shifting if you need to use it sometime. So as I'm queuing stuff to this new buffer, I'm adding to this n size. By calling it this way, n size plus, one, it initializes where we are in the array at that time, but it also keeps track of this n size so that later, once I'm out of the switch statement, and I've computed my cyclic redundancy check that I'm not going to use, I don't believe, at this moment, I get down to this for loop, and it is for I is less than n size. So then I'm going to write all of this serial information for as many things as I stacked up in that buffer. So this is where it comes down to the reason I couldn't use the original, well, not the original, other people's created libraries for this. The ESP32 basically would send this, it would pull the data pin low using one of the pre-can libraries. It would pull the write and read enable pins low before it was done with the packet. And then obviously the VFD would say, well, I'm missing information at the end here that's corrupted packet, and it wouldn't take the information and act upon it. So that video that I mentioned, which is up in the wiki, I believe right here, if you click that video link, take you to that guy's video, and he was talking about this, and he happened to find a sweet spot for the amount of time that we want to pause after we write. So I put that delay in microseconds, which I believe is, or not microseconds, milliseconds. Nope, it is microseconds. I believe that was 120 microseconds. So once I have written this packet, you'll hear the VFD fire up, and then we continue through that web server command, which in the handle stop function, where did I put that? So it's going to also send the server the stopping, but before we do that, there should be the FN stop, I thought. I'm updating the OLED. Sorry, 1 second here. I'm trying to figure out where I was actually calling that. Maybe it's in my right function, actually. Well, somewhere for sure I'm updating that because I know it works. But basically, so once we have sent the Modbus command, then we're updating the OLED, and on the server request side, we are doing a server send with whatever this string information is. So when I click the thing to do whatever, like reverse, we see that it updates this running reverse. That's coming from that. So that's the last thing it does in that function whenever it gets that HTTP request, so you know that it has done everything else up until this point. You can see there's almost no delay. That's the reason that I want to update it in the future, because we can make use of the multiple cores and basically just run the handle server on one core while we can run the serial buffering on the other core. That way we don't have interference and lag or system critical failures because it's waiting on a web request thing to process while we're doing Modbus things. So this is at 12 minutes already. I'm going to go ahead and stop it. I will continue to update the project, and I have applications in mind, so keep your eyes out for the next one. Thanks.